Welcome, viewers of Science and Spirituality. Today we will be meeting Dr. Federico Capasso, a Robert L. Wallace Professor of Applied Physics at the Harvard School of Engineering and Applied Sciences. Over the years, Professor Capasso has become primarily known from his pioneering work on novel quantum devices such as avalanche photodetectors, which are light sensors that process optical communications to electrical signals, resonant tunneling diodes, ultra-fast transistors, and other semiconductor devices. The quantum cascade, or QC laser, is an innovation Professor Capasso and colleagues developed in the early 1990s. This technology holds promise for important applications such as sensing gas and liquid vapor molecules in various environments with ultra-high sensitivity, even to the degree of 1 part per billion. Given that we live in times of accelerating global warming, our world needs such a tool, especially for measuring the greenhouse gas concentrations in the atmosphere. Supreme Master Television interviewed Dr. Capasso to learn about the highlights of his scientific journey through the world of quantum devices and how these tools can impact our lives. Dr. Capasso begins by giving us a bit of his background.
I got my doctorate over in Italy in the late 70s. I got a fellowship for the US for 9 months. So I decided to go to the Great Bell Laboratories that for decades has been essentially the primary industrial laboratory in the whole world. 7 Nobel Prize winner. It invented the transistor, the laser, the fax machine, the feedback circuit, a stereo sound, and so forth. And I ended up staying there for 27 years. I was a researcher for about 10 years, and I became a manager. And my last 2 years where I was vice president for physical research. And at the end of my 27th year there, I decided it was time to do something else. I moved to Harvard, and I'm having a great time.
Starting from the early 1980s, scientists were able to implement quantum wells, resonant tunneling, 2- and 1-dimensional electronic systems, with electrons barely subjected to impurity scattering because semiconductor materials could be made so pure. This was thanks to a powerful crystal growth method called molecular beam epitaxy, or MBE, capable of growing high crystalline quality thin layers with atomic accuracy and high material purity. Thus, at that time, scientist engineers like Federico Capasso had access to resources to create imaginative quantum devices based on abstract ideas taken from quantum physics textbooks. They also explored new avenues of electronic and photonic devices, practically limited only by their imaginations.
The idea basically is, you see, using the laws of quantum mechanics, you can think yourself like a modern alchemist. You can, using the laws of quantum mechanics, grow materials in a controlled way so that you can create materials with man-made properties. And in fact, the quantum cascade laser is an exercise in design of a new class of laser material. Nature is involved because it dictates the laws of quantum mechanics, but essentially women and men are really the designers behind it. Okay, we design things so that a new material has certain properties that you cannot find in nature.
For many decades, double heterostructure laser diodes have been manufactured, and this technology greatly advanced the world's semiconductor and telecommunication industries in the 1980s and 1990s. German scientist Dr. Herbert Kromer and Russian scientist Dr. Zoris Alferov were named Nobel laureates in physics in 2000 for developing semiconductor heterostructure lasers and other devices used in high-speed optoelectronics. In 1994, Professor Capasso and his Bell Labs colleagues invented a new type of laser family called the quantum cascade, or QC laser, which can be pictured as an electronic waterfall flowing down a staircase. At each step, a photon of a certain wavelength is emitted. Another special attribute of this laser is that wavelength emissions can be altered over a broad wavelength range in the mid-infrared wavelength range 3 to 12 micrometers, where it's not easy to find alternative efficient light sources. And it is an important spectral range because that is where most molecules have exhibited their absorption and luminescence spectra, thus allowing the laser to be used for chemical analysis.
And the semiconductor laser essentially has entered everyday life. I mean, when you listen to music on a DVD, basically what reads the DVD is a semiconductor laser. Okay, it's also used for telecommunication. We wouldn't be seeing high-speed communication. The fact that we can literally transmit the Encyclopedia Britannica in maybe just a few minutes of a high-speed cable without a semiconductor laser, because what it does, it emits pulses of light that are on and off. They represent bits. Now, the semiconductor laser is based on a very simple principle, basically, that the wavelength that it emits depends on the chemical properties of the material. So if you want to have a blue laser, you choose a material called gallium nitride. But if you want an invisible semiconductor laser like you use for telecom type of application, you have to change the material and use complicated alloys. It's called the indium gallium arsenide phosphate. So you want to change the color of the laser, you have to change the material.
Professor Capasso noted that the quantum cascade laser is a huge step forward in terms of laser design.
Basically, you control the wavelength, not by changing the material, but by changing the thickness of an ultra-thin layer inside the active region. The active region is the region that emits the laser light. And so it is designed to cover primarily the so-called mid-infrared spectrum. This is the spectrum where the molecules have their telltale absorption fingerprints. Molecules like carbon monoxide, carbon dioxide, water, and so forth. Okay, so the mid-infrared is a potentially extremely important technological area, because using these invisible wavelengths, you can detect molecules. So these lasers detect very low concentration, parts per billion in volume trace gases. This could be good trace gases, they could be bad ones, toxic ones. So the application are potentially huge of this laser.
When Science and Spirituality returns, we'll explore more on how the quantum cascade laser could be used as a tool to measure pollutants in the atmosphere. Please stay tuned with us. Welcome back to Science and Spirituality, where we have been hearing from Professor Federico Capasso about the invention of the quantum cascade laser. This tool can emit coherent light in the mid-infrared range, where many gas and liquid molecules have their characteristic absorption spectra. Even 1 molecule per billion can be detected using this novel laser light source in various environments. Let's continue the quantum cascade laser story with our guest, Professor Capasso.
This is the heart of the quantum cascade laser. You see, by controlling this very thin layer, you are seeing a cross-section. Take a cross-section of a cake or a sandwich. These are the layers of these sandwiches. So what happens, you inject current. This is the blue arrow, and you have an electron, which is a unit of electrical current, stumbling down this energy staircase. At every stage, you emit a photon. And so one electron traverses the energy staircase, you have 10, 20 photons per electron. So this can be a very powerful laser. We are collaborating with a company in California now, Pranalytica, and we made this very powerful laser with them that gives out 3 watts of power in actual continuous wave at a mid-infrared wavelength.
Dr. Capasso next speaks about other real-world applications of the laser.
This is a beautiful collaboration we had with Ford Motor Company. So we want to make sure that cars do not emit too much bad gases, like carbon monoxide and nitrous oxide and so forth. Now, in the future, as the problem of climate and pollution become more severe, the rules, at least in the US, they will become more and more stringent. So we are looking to be able to measure parts per billion of certain gases in the exhaust of automobiles. This is another beautiful type of application. We are collaborating here at Harvard with one of the world leaders of atmospheric chemistry, Professor Jim Anderstone. He was instrumental in writing the Montreal Protocol for the ozone. We are starting to send our laser in the actual stratosphere and in the atmosphere to measure tiny concentration of gases. These are like methane that are markers of the jet stream. It turns out if you measure the concentration with height of these gases, you can determine the path of the jet stream. And in fact, this is a collaboration we did with NASA. This is an aircraft that went up to, 20,000 kilometers. And our QC lasers were right here under the wing, and we measured the concentration of methane at part per billion level. As the aircraft was going up and diving down, we need to understand climate. This is a very serious problem. For example, this is a model that tells what the sea level rise induced by global warming could do to Greenland. You see, this is a scenario of Greenland melting. 3-meter sea level rise, it could be serious. So climate is affected also by the circulation of even small concentration of gases in the atmosphere. And so the idea here is to send our QC laser. These are the UAVs, unmanned vehicles. There is no pilot. The QC laser will be sitting here and measure very tiny concentration of these gases to understand essentially their effect on climate. Eventually, we need predictive model of climate, so these type of measurements can help in this direction.
It appears the quantum cascade laser can help better our world in many ways, especially in the area of climate change. We thank Professor Capasso for sharing his insights on this high-level technology that he helped develop. Please join us next Monday for part 2 of our program, where Dr. Capasso will discuss the esoteric Casimir-Lifshitz effect with us. Coming up next is Words of Wisdom, right after noteworthy news, here on Supreme Master Television. May your life be blessed with God's love, comfort, and light.